Harvard astrophysicist Avi Loeb has suggested the 3I Atlas is actually some type of alien technology. 3I Atlas, the interstellar comet racing through our solar system right now, isn't alone. Scientists have picked up signals of 9 other objects trailing in its path, a discovery that raises more questions than answers. Are these fragments? Are they part of a larger stream of interstellar debris? Or are we watching something entirely new unfold in real time? One thing is certain. 3I Atlas is not the comet scientists expected, the stranger in the dark. Most comets play by the same rules. As they get closer to the sun, they warm up, they grow a tail, and they move along orbits that bring them back around eventually. 3I Atlas isn't doing that. From the very first time astronomers spotted it, the numbers didn't fit. It was moving too fast on a path that nothing in our solar system could control. That's when it became clear this wasn't one of ours. This was only the 3rd confirmed interstellar object we've ever seen, and right away, it was already breaking expectations. And here's the wild part. In just the last decade, we've gone from seeing none of these visitors to suddenly spotting 3. First came 1I Oumuamua in 2017, then 2I Borisov in 2019, and now Atlas in 2025. Each one has been its own kind of weird. Oumuamua looked like a long shard of rock with no tail at all. Borisov looked more like a regular comet, but its chemistry was off. And Atlas? It has a glowing tail, but the details don't line up with anything we're used to. It shines in colors that shouldn't be there, and it moves without showing the usual push that gas jets give to comets. That's what makes Atlas so important. It's not just another rock flying through space. It's a sample of another solar system drifting through ours for a short time, carrying ice, gas, and dust we've never seen up close before. And unlike Oumuamua, which slipped away before we could study it properly, Atlas is sticking around long enough for the world's biggest telescopes, Hubble, JWST, Gemini, and more, to lock on and pull out every clue they can. Not our first, but the weirdest yet. When you line 3I Atlas up against the 2 interstellar visitors we've already seen, that's when things start to feel even stranger. Oumuamua was the first back in 2017. It zipped through so fast that we barely had time to look at it. No tail, no visible coma, just a long, flat object reflecting sunlight in a way that confused everyone. Some thought it was a piece of rock torn from another world. Others went further and wondered if it was a fragment of something artificial. Whatever it was, it came and went before we could get clear answers. Then came 2I Borisov in 2019. This one looked more like what we expected. It had the classic comet tail, the dust, the gas, but even then, its chemical mix was off. It was richer in carbon monoxide than most comets we'd seen before. That made sense if it had formed around a star much colder than ours. But still, it was another reminder that interstellar comets don't follow the same recipe. And now, there's Atlas. At first glance, it looked like Borisov's cousin, a comet with a glowing tail, releasing gas as it warmed up. But as the observations piled in, it started to break the pattern all over again. The way it shines, the gases inside it, even how it interacts with sunlight, none of it lines up neatly with either Borisov or Oumuamua. If anything, Atlas feels like a mix of the two. It has a bright coma like Borisov, but its behavior has left scientists scratching their heads the same way Oumuamua did. That's why Atlas is being watched so closely. With Oumuamua, we were caught off guard. With Borisov, we got lucky, but it faded fast. But with Atlas, the timing is better. We've got the instruments, the data, and the experience from the last 2. It's our best chance yet to figure out what these wanderers really are, and maybe even where they're coming from. One of the first things that made 3I Atlas stand out was its color. Most comets look white or slightly bluish when you see them through a telescope, but Atlas developed a green glow that quickly became its signature. Normally, that kind of glow comes from a simple cause, molecules of C2 gas breaking apart in sunlight, which makes comets look green as they get closer to the sun. It's such a common effect that astronomers use it as a kind of marker for comet chemistry. But with 3I Atlas, that explanation doesn't fully work. When telescopes tried to measure its gases, the signs of C2 weren't nearly as strong as they should have been, and yet the green color was there, clear as day. That means something else in the coma is producing the glow, or that Atlas has a mix of gases we haven't seen acting together before. Either way, the simple answer, it's just C2, doesn't hold up. The mystery deepened during the September lunar eclipse. Under dark skies, cameras captured Atlas glowing a vivid green, brighter and more obvious than expected for its distance from the sun. The fact that it showed this glow without the usual molecules being confirmed has left astronomers debating what's really going on inside it. Some suggest there could be faint amounts of C2 hiding below detection limits. Others think another gas, maybe related to its heavy load of carbon dioxide, could be playing a role. The chemistry of 3I Atlas is one of the clearest signs that this object doesn't belong here. When telescopes measured the gases in its coma, water was not the main ingredient. Instead, carbon dioxide dominated the mix. That balance is unusual compared to the comets of our own solar system. For most comets here, water ice drives the show. As they get close to the sun, it vaporizes, filling the coma and shaping the tail. Atlas is different. Its carbon dioxide levels are far higher than expected, with water playing a smaller role. This difference points to its origin. In colder regions around distant stars, carbon dioxide can freeze in bulk, while water remains less active. A comet born in that environment would carry a signature that doesn't match the bodies we know. That's exactly what Atlas is showing us. It is physical evidence that other planetary systems build their comets with a different recipe. Along with carbon dioxide, astronomers have picked out carbon monoxide, traces of water, and signs of icy grains among the dust. The balance is messy, but the ratios are not like the ones measured in local comets. It confirms that Atlas comes from a world with different conditions, where the balance of gases and ices followed another set of rules. This is the value of Atlas. Every spectrum and every reading adds a piece to the picture of how other solar systems work. It is not theory, not a model, but an actual sample from somewhere else in the galaxy passing through our reach just once. Another surprise from 3I Atlas came when astronomers studied how sunlight scatters off its dust. Normally, comets in our solar system show a familiar pattern. At small phase angles, where the sun, the comet, and the observer line up almost straight, the light tends to polarize in a predictable way. This polarization tells scientists about the size and structure of the dust grains drifting in the coma. Atlas didn't follow the pattern. Instead, it showed what researchers called extreme negative polarization. In plain terms, the light coming off it behaved in the opposite way to what's seen with almost every other comet. The degree of this effect was larger than usual, and the angle at which the polarization flipped was also different. For scientists who rely on polarization as a tool to compare comets, this was a red flag. It meant the particles making up Atlas's dust are not like the ones we're used to. The most likely explanation is that the dust contains an unusual mix of ice and fine particles. Some suggest fluffy ice grains, fragile clusters that scatter light differently than compact dust. Others think the composition itself could be alien, carrying materials we don't see in large amounts in our own comet populations. Whatever the case, the way Atlas reflects light is not normal. This makes sense if Atlas formed under conditions far from what shaped comets here. Light scattering is a direct clue to particle properties, so this anomaly is more than a curiosity. It is physical proof that the dust around Atlas doesn't match the template we know. In other words, even the sunlight bouncing off this object carries the signature of another solar system. Most comets show a small but measurable effect as they move through space. When sunlight warms their surfaces, jets of gas and dust shoot out. These jets act like tiny thrusters, giving the comet a non-gravitational push that changes its orbit slightly. Astronomers can usually detect this effect in the data, even if the change is very small. With 3I Atlas, that push hasn't shown up. Despite the obvious coma and tail, its motion looks almost completely governed by gravity alone. Observations taken over thousands of points from May through September 2025 have not revealed the kind of acceleration seen with other active comets. The absence of this effect has led to competing explanations. One view is that Atlas is simply very massive. If the nucleus is several kilometers across and dense, the small thrust from outgassing would be too weak to shift its course in a way we could detect. Estimates based on this idea suggest it could weigh tens of billions of tons. Another possibility is that the gas jets are balanced in opposite directions, cancelling out any net push. If Atlas vents in a symmetrical way, Its overall path would stay smooth even though material is leaving the surface. The debate matters because it touches on the most basic question: how big is Atlas really? If it is as large and heavy as some suggest, as if the outgassing wasn't influencing it at all. There are a few ways to make sense of this. One idea is simple scale. If the nucleus of Atlas is very large, perhaps over 5 kilometers across, then the small jets of gas leaving its surface would barely budge it. Calculations based on this assumption give a mass of more than 30 billion tons. To put that in perspective, that's heavier than several Mount Everests combined, all packed into a body racing through our solar system from another star. Another explanation is symmetry. If Atlas is venting in a balanced way with jets firing from multiple directions that cancel each other out, then the overall push would vanish in the data. The comet would still be losing gas, but the motion would stay smooth, hiding the usual signs of acceleration. Either scenario makes Atlas unusual. A comet this heavy would be unlike most of the smaller, fragile bodies we know, and a comet with such perfect symmetry would also stand out, since natural surfaces usually vent unevenly. That's why the missing push has become one of the central debates about Atlas. It forces astronomers to consider whether this object is larger and stronger than expected, or whether it's revealing a type of comet behavior we've never properly seen before. The clash over size. If there's one question that keeps coming up with 3i Atlas, it's how big this thing really is. Size isn't just a number on paper. It tells us how much material the object is carrying, how powerful its outgassing should be, and how far away we can still track it with confidence. But right now, the numbers don't agree, and that has sparked one of the liveliest debates around Atlas. The Hubble Space Telescope has put an upper limit on the nucleus at about 5.6 kilometers across. That's large by comet standards, but still in line with the biggest solar system comets we've studied. The problem is, the nucleus itself is buried under a bright coma, which makes it nearly impossible to separate the solid body from the glowing cloud around it. So that figure might just be a ceiling, not the actual size. Some astronomers argue the true nucleus could be much smaller, maybe closer to a few hundred meters, hidden under the glare. Then there's the other camp, boosted by Avi Loeb's interpretation of recent data. Looking at the missing push, the lack of measurable non-gravitational acceleration, Loeb and his team suggest Atlas must be far heavier than it looks. Their calculations point to a mass of at least 33 billion tons, which would only make sense if the nucleus is several kilometers across and unusually dense. In that scenario, 3i Atlas would be one of the most massive interstellar bodies ever detected. The truth is that both sides have valid points. If Atlas is small, then its gas release must be balanced in a perfectly even way to explain the missing acceleration. If it's big, then we're dealing with a massive object that dwarfs most comets we've tracked. Either way, it challenges the standard picture. And for astronomers, the disagreement isn't just academic. The actual size of Atlas will shape how bright it might get near the sun, whether it can survive perihelion, and how much of its material we can study before it disappears back into deep space. The tail that won't sit still. Every comet grows a tail when sunlight heats its surface. But the tail of 3i Atlas has been especially restless. Images from Gemini South, amateur telescopes, and even wide-field sky surveys all show the same thing. The tail is stretching, shifting, and changing faster than most expected. In some photographs, it looks broad and diffuse. In others, it sharpens into a more defined streak. Some observers have even captured rainbow-like color spreads in the coma, the light scattering through dust and gas in ways that look almost painterly. These changes aren't random. They come from a mix of forces acting on the dust and gas escaping the comet. Solar radiation pressure pushes particles into long streams. The solar wind bends them, and the rotation of the nucleus affects how the material escapes. But with Atlas, the scale of the changes seems more dramatic than with the average comet. Within days, the structure of the tail can look noticeably different, hinting that the comet's venting is uneven or perhaps unusually active. The rapid growth of the coma also adds to the picture. As Atlas moves inward, more surface ices are exposed and more material escapes. That expansion makes the tail both brighter and harder to define, creating a moving target for telescopes. For scientists, these swings are valuable data. They can reveal how the nucleus rotates, how the gases interact, and how the dust grains scatter. For the rest of us, they make Atlas one of the most photogenic objects in the sky. Right now, what makes this even more important is timing. As Atlas gets closer to the sun, its activity will only increase. That means its tail may grow larger, more fragmented, and possibly split into multiple streams. For astronomers, this behavior is not just a spectacle. It's a chance to study how an interstellar comet responds to solar heating in real time. And for everyone watching from Earth, it's a reminder that Atlas isn't just drifting silently through space. It's actively changing before our eyes, reshaping itself every week as it races toward its closest approach. All of the questions around 3I Atlas, its chemistry, its dust, its missing push, even its size, are building toward a single moment. On October 29th and 30th of 2025, Atlas will reach perihelion, its closest point to the sun. 3I Atlas is only the third interstellar object we've ever confirmed, but the pace is telling. In less than a decade, we've gone from none to 1I Oumuamua in 2017, 2I Borisov in 2019, and now Atlas in 2025. If 3 have crossed our paths this quickly, it suggests there may be many more out there, slipping past unnoticed or too faint to catch with current telescopes. The galaxy is full of shattered planetesimals and frozen debris, and our solar system is not sealed off from them. That's it for today. Let us know in the comments down below what you thought of this latest video on 3I Atlas. Don't forget to like and subscribe for more space content.